I'm going to discuss the convergence problem for power series. So given a power series, or we can think about given a function, maybe we'll call it g, defined by a certain power series, we want to ask what numbers can we plug in to the power series? What numbers can we plug into this formally defined function g? We want to know what's the domain of the function. Alright, so we're going to figure that out for each of these two examples. Okay, that's going to be called the interval of convergence. Okay, so going over to the scratch paper, I've got the series written down. We want to answer this question. Right now, to answer this, we're going to notice that this series is in fact a geometric series. After we do a small rewrite, we're going to just factor the exponent k off of each factor here and rewrite this series as the sum from 0 to infinity of 2 times x all raised to the k power. So we're thinking about the ratio here, the common ratio from one term to the next as being 2x. We called that r before. Right, but that's the main observation for this particular series, is that since it's a geometric series, we know exactly when it converges and when it does not converge. It converges only if that ratio is between -1 and 1, only if that ratio is less than 1 in absolute value. All right, now that means that our ratio 2x has to lie strictly between -1 and 1. All right, now solving this inequality for x, divide both sides by 2, we get that x has to lie between -1/2 and 1/2. So that's it. For this series, the domain of that series, or if you want to think about this as a function, g of x, or function g defined by that power series, is valid, or it's only defined over the interval from -1/2 to 1/2. Now, something that's kind of a subtle point here is that since we know this is a geometric series and we know when it converges, we can write a formula for it down. That's the one very special thing about geometric series. We can write the formula for it down. So we know from our previous work that the formula is 1 over 1 minus r. So we can have 1 over 1 minus 2x and say that power series is equal to that for only for x is between -1/2 and 1/2. So this series is equal to this function only for those numbers. However, just notice this formula here is defined for lots of other numbers besides those in between -1/2 and 1/2. So that's kind of a peculiarity. Okay, now let's go back to the second problem before I finish it on the scratch paper. We want to look at this series. Now we want to know, same question, what numbers can we plug in? What numbers can we not plug in? Look at this formula. This is not a geometric series, so we're not going to be able to apply the same ideas that we just did in the last example. We're going to have to do something different. All right, and typically what we're going to do is use the ratio test. In fact, the ratio test for absolute convergence. Okay, so that's what we're going to apply in this example, just rewriting it over here. The series is starting at k equals 1, and it's 1 over the square root of k times x minus 4, the quantity x minus 4 to the kth power. All right, now we want to answer that question. What's the domain? All right, so what is the interval of convergence for this power series? We want to know what x's can we plug in, what x's can we not plug in. We're going to be able to answer that. And the reason we will be able to is that because we know from our previous work for any series, okay, power series or not, or just a straight numerical series, absolute convergence implies convergence. So what we're going to do is test for absolute convergence, okay, and see what that gets for us. See what information we can glean from that. So in testing for absolute convergence, we're going to write the ratio of the absolute values from one term to the next in our series. So we're going to plug in k plus 1 instead of k. So we get 1 over the square root of k plus 1 times x minus 4 to the k plus first power over the absolute value of 1 over the square root of k times x minus 4 to the kth power. Now these numbers, 1 over k plus 1 or 1 over the square root of k, those are positive quantities, so we can pull them outside the absolute value. We can take the absolute value of x minus 4 to the k plus first power on top, and we can pull out the exponent. right? Raising it to a certain power, positive power, it's the same as taking the absolute value of x minus 4 first and then multiplying it by itself, k plus 1 times. Similar on the bottom, it's the absolute value of x minus 4 to the kth power. And then we just simplify. So we're going to multiply by the reciprocal after we simplify a little bit. So cancel out k factors from the top and bottom. We're left with 1 on top. And then we multiply by the reciprocal to get square root of k over square root of k plus 1. Now we can rewrite this as 1 square root of the quotient on the inside. So it's the square root of k over k plus 1 times absolute value of x minus 4. Then we could do polynomial long division here to rewrite this on the inside as 1 minus 1 over k plus 1. What we really want to do is take the limit as k approaches infinity. We can see on the inside this quantity, if we look at the degree of the polynomials on top and bottom, they're both 1, so that quantity is going to approach 1 as k approaches infinity. Or we can rewrite it like this and see the same thing. So now what we're concerned about is for the ratio test for absolute convergence, we're looking at the limit as k goes to infinity of the ratio of the absolute values of one term to the next. That's the same as the limit of square root of 1 minus 1 over k plus 1 times absolute value of x minus 4. As k goes to infinity, we just get the absolute value of x minus 4. Now for the ratio test, we're really concerned about when is that ratio, the limit, less than 1 of those ratios. That's going to be true if the absolute value of x minus 4 is less than 1. Now that's the same as saying that the absolute value of x minus 4 has to be between negative 1 and 1. Adding 4 to both sides here, we get that x has to be between 3 and 5. Okay, typo here, not negative 3. It's between 3 and 5. Okay, so now that's what the ratio test for absolute convergence tells us. What we need to do from here, though, is to answer the question, what happens when this ratio is equal to 1? That is, what happens at the endpoints. We got to double check here. All right, so I fixed my typo. So we need to actually test the endpoints of this interval, this open interval. At x equals 3, we're going to just plug 3 in for x and see what we get. So we get the sum from 1 to infinity of 1 over the square root of k times 3 minus 4 to the kth power. 3 minus 4 is negative 1, so it's the sum from 1 to infinity of 1 over the square root of k times negative 1 to the k power. From here, we know that this series converges because it's a piece series. We've got the square root of k on the bottom, but it's an alternating piece series. Right? That's the key. So the square root of k on the bottom, that would be bad unless it's an alternating series. It would not converge unless the terms alternate, but they do. So the terms go to 0 individually, and they alternate, and that tells us it's convergent. So it's going to converge at x equals 3. At x equals 5, we plug it in, we get 1 to the kth power there. So that's just 1 for any positive integer k. So we just get the series 1 over square root of k. Now that's a piece series with p equals 1/2. And that's, therefore, divergent because we need the power to be bigger than 1 for convergence via the integral test. So what do we conclude? The series converges at x equals 3 and diverges at x equals 5. So if we think about this function, g of x, which is defined to be this power series, that's only valid for numbers between 3 and 5, and only at 3 can we plug in on the endpoints. All right, so the domain is half closed, half open interval from 3 to 5, including 3, not including 5.